So first, I would like to thank all the organizers, A, for organizing this wonderful meeting, and B, then, giving me a chance to share some of our recent work with you. But before I start, let me also add my words of thanks to those of Samriddhi's. The ICTS team has, as always, done a wonderful job, and I'm really grateful to them, and I would like to thank them on behalf of all the speakers, participants, everybody. So thank you very much. It's been a long week, so I will not tax you too much. I will talk about particles and fields and turbulence, superfluids, binary fluids, and active fluids. Most of the talks in this meeting have concentrated on the complexity that arises by looking at different types of particles, typically. More complex shapes than spherical and so on. This talk is going to keep simple particles, typically passive, unless I get to the last part of my talk, and then makes things complex by changing the fluids, the hydrodynamical systems that we are talking about. So this work, the work that I'm talking about has principally been done with Sanjay, Nadia, and Kiran, and also Anupam, Akhilesh, old work with Vishwanath, Akshay, and Mark. I don't know whether I'll get to that work today, but we'll see. All right, so what is the work that I'm talking about? Here are some references. This paper is on the archive, which is our recent work on superfluid turbulence. This paper on binary fluid turbulence is in preparation. And this paper on irreversibility in bacterial turbulence is also available on the archive. These are some old papers. I might or might not get that far, but had I had enough time, this would have been a nice way of ending the talk. Let's see. All right. So here's, introduction. Then I'll tell you about the fluids, the fields, and the particles, results and conclusions. So here's the first system that we will be looking at. So let's say superfluid helium, in general any superfluid. But these experiments done by this group show superfluid helium, and there are images of particles. So it's important to consider systems in which there are both particles and the fluid, in this particular case a superfluid. This is just above the transition temperature, and then you see branching filaments, and you see complicated vortex and particle interactions. The particles, at least in this particular experiment, were all frozen deuterium or tritium, I think, if I'm not mistaken. But they were quite a bit larger than the vortex core size, although more small particles might have been developed now. I think have been developed now. Here is a recent paper which looks at so-called counterflow turbulence in superfluids. In superfluids, you can have two types of turbulence, one in which the normal fluid and the superfluid move in the same direction, and one in which they flow in opposite directions because you heat it in such a way, and then suitable momentum conservation, etc., says they must go in opposite directions. This will become clear when I write down the model. Okay, so you can see that the experimental groups, a very, very distinguished combination of scientists here, are interested in such problems which require the interaction of particles with superfluids in the turbulence context. The other systems that I will talk about have been alluded to off and on in this meeting. These are examples of binary fluids flows. Of course, there are clouds, which everybody would like to understand. So here is a photo, and here's a schematic, a typical raindrop. So at the moment, I guess I'm only thinking of warm clouds. And then there are other examples. These have also been talked about in this meeting, droplets of oil in water or bubbles. There was a very nice talk that Prasad gave. And here is an example of an anti-bubble, which is a low-density fluid inside a high-density fluid. So, you know, they form all sorts of exotic objects, often in turbulent flows. In today's talk, I don't think I will get to the anti-bubbles, but okay, some other day. The last system that I will talk about is an example of an active fluid flow. In fact, the simplest model for an active fluid. This sort of turbulence has been gaining a lot of attention over the past decade or so. You can see there's already a review in annual reviews of condensed matter physics. This is a bacterial suspension of Bacillus subtilis. And without any external forcing, there is a complicated turbulence-like pattern. And here they have abstracted a vorticity field, which you can see here. So in this talk, I will try to cover simple models for these different types of turbulence. And then we will include particles in those models and see what the statistical properties are of those particles when they're advected by such turbulent flows. So of course, all of you know this, but I'm just putting it here for the sake of completeness. First of all, what is superfluid turbulence? I mean, they say, at least they being Feynman said, it's a tangle of quantized vortices. And here is a nice picture taken from this website showing a tangle of vortices. Each vortex has the same circulation. This is conserved. And superfluid turbulence has been found in superfluid helium-4, helium-3 are also in Bose-Einstein condensates. Excuse me, I'll take off my mask. Please hold on for a minute. Okay. So you ask, how should we describe a superfluid? Well, it really depends on the level of description that you want to employ. At the most microscopic level, there would be, I mean, you can be even more microscopic than this, but Gross-Pitayevsky equation. This is good for a low temperature weakly interacting Bose gas. It accounts for phenomena at the length scale of the superfluid vortex core with a healing length psi. If possible, I will say a few words about this at the end. Then there is a vortex filament model. That tangle of vortices that I showed you earlier is from such a simulation. It distinguishes between individual quantum vortices. It ignores the natures of the vortex cores, and it is valid on length scales greater than psi, and it's in the incompressible limit. Then here is an old model, Hol-Painen-Becharevich-Halatnikov. It's a two-fluid model. It does not resolve individual quantum vortices. It's sort of macroscopic, has a classical vorticity field, which assumes that there is some polarization of quantum vortex lines so that you have a continuum description in terms of conventional fluids. I will tell you in a minute. Then there is a kinetic theory model, and there are wave turbulence models. And the color code here is that I will say nothing about the blue models, but I will talk only about the ones which are written in red. So most of what I have to say about turbulence in superfluids with particles is contained in this preprint, which we have on the archive. And I already told you about counterflow turbulence. So in this, Akhilesh did all the work for coflow, and Sanjay Shukla did all the work for counterflow. And of course, it came out of earlier work of Vishwanath and Akshay, etc. So what are these equations? Some of you might have seen them before. It's basically Navier-Stokes for the normal fluid. The subscript N stands for normal, and the subscript S stands for superfluid. And here's standard viscosity. There is an external force, And there is a so-called mutual friction force, which I will tell you about in the next slide. I won't explain it because this talk is too short to explain the form, but I'll tell you about it. And over here, we have put in a small viscosity even for the superfluid. Of course, the superfluid should have no viscosity, but in this model, people say that this takes care of vortex reconnection and so on at some scale. In any practical situation, of course, nu sub s should be much less than nu sub n. Now, un and us, the capital ones, could be the mean velocities of these externally imposed. They vanish for co-flow because we can always go to a frame where they vanish. But for counterflow, we will have a difference between them, which we cannot get rid of. And this will be an important control parameter in the case where we are discussing counterflow turbulence, which we can non-dimensionalize by dividing it by some root mean square velocity. And so the goal is to study this in the statistically steady state of turbulence in the three-dimensional Holbein-Becharevich-Halatnikov model. Okay, I told you about the mutual friction force. This is basically leads to energy transfer between the normal fluid and the superfluid components. I won't explain all these terms here. There's the superfluid vorticity and the difference between the normal and superfluid velocities. So you see that if they're equal, then there is nothing. And rho is the total density, and so on. And these coefficients, it might look like there's a large number of coefficients, but thanks to the work that I think Barengi did for his PhD, these have been measured. B and B prime and rho n and rho s have been measured as a function of temperature. So in our studies, we will use the data from those studies to tell you at which temperature we are running this. And there's all low Mach number flows, so there's incompressibility for both these fluids. Okay, now how do we put in the particles? Well, we put in the particles. If we will do, typically we will do heavy particles, but we'll also allow for light particles. So these are the Maxey-Riley-Gatignolle equations, which you've seen several times in these lectures. And these can be generalized to the case of this HVBK system. So instead of just having U minus V over tau, you will have one term coming from the normal fluid, another one coming from the superfluid. And this is the term which allows you to put in lighter particles if necessary, which might be relevant to the experiments in helium because you're using frozen deuterium, etc. Though it's a bit unclear to me because depending on the sizes of the particles, but here it's only the density which enters. Okay, so we know how to do direct numerical simulations, as does everybody else in this meeting. So we use the pseudospectral method, and we use the Eulerian velocity fields to update the particles, and we use interpolation where necessary. So we use nu n over nu s less than 10. So ideally you would like nu s to be as small as possible, but in any practical calculation you cannot make it arbitrarily small, otherwise your code will blow up. Okay, but we do the best job we can. The first thing to note is, of course, the energy spectra for the co-flow case look very much like those of classical fluid turbulence. In fact, for a long time, people have said, it goes back to experiments of Turbulence, saying there's very little difference between superfluid and classical turbulence. Now, of course, you can always find things which agree and things which don't. So co-flow spectra look very much like their classical fluid turbulence counterparts. But when you have counterflow, obviously there will be anisotropy. And if there's anisotropy, you have to distinguish between K parallel and K perpendicular. The K perpendicular spectra you can average over shells in 2 dimensions. So you see a -8/3 spectrum. And for the parallel one, because you don't average, you get a -11/3 spectrum. This has also been noted in a recent paper by this group, which has appeared just early this year. And I'm showing you data from 2 different values of the counterflow velocity. And you can see there's a clear difference between K perp and K perpendicular and K parallel, as it should be. Now you can ask, what do the particles do? So I have over here slightly complicated pictures. The red isosurfaces show you isovorticity contours, and these are at different Stokes numbers for the yellow particles. And you can blow up these regions, and for the co-flow case, which is slightly below the transition temperature, so it is in the superfluid, you know, they are basically like they would be in conventional fluid turbulence. Some details might be different, but it's like this. But in the case of counterflow, and here this I'm showing you a simulation where we have a square cuboid domain so that we allow for the anisotropy. These things get pulled out. You can see that the vorticity isosurfaces get pulled out, and indeed even the particles get pulled out in the direction of UNS. All right. If so, then what? Well, studies of inertial particles in superfluid turbulence, if I compare them with the huge number of studies that have been carried out for classical fluid turbulence, are in their infancy. While we were doing this work, there was also some work from the group of George Apostolovich and his postdoc Polanco, who studied clustering of inertial particles in such flows. We have looked at a very large variety of properties, statistical properties of these particles, which we have, you know, based on the earlier work we have done in classical fluid turbulence. So we characterize these by various probability distribution functions. For example, there is a PDF of the mean angle between particle positions. So if you look at 2 nearby positions, then if they're separated by time tau, the mean angle is theta, you can get a PDF of this. Similarly, when you have particle trajectories, you can calculate their curvatures and torsion, and you can get PDFs of those. You can ask whether for a heavy particle, let us say, what is the angle between the Eulerian velocity and the particle velocity? Let's call that phi n for the normal fluid and phi s for the superfluid. We can get CPDFs for these. Then if you get more technical, you can obtain persistence times. I won't cover this in great detail, but again, I'm sure all of you know about the Q and R invariance in 3D turbulence. You can get the HVBK analogs of those. In certain regions which are called A and B, you can say the flows are essentially vortical, and therefore you can ask the question and answer quantitatively how long particles spend in vortical regimes. You can also characterize irreversibility of 3D HVBK turbulence by looking at statistics of the power. This was mentioned briefly in one of the talks. I will cover it here and also in the context of bacterial turbulence. Then there are various first passage times. There are also velocity structure functions. To the best of my knowledge, such a detailed study has not been attempted before. I will not show you every detail, even though I have much of it on my slides, because it's not so easy to take in so many PDFs all at once. But all I want to show you is that, for example, this mean angle between particle positions, the qualitative form is similar to what is obtained in classical fluid turbulence, but there are detailed differences, more so for the case of counterflow. And we have studied this not only for heavy particles, but also for light particles. And you get similar scaling regimes, in these CPDS. You get scaling regimes with exponents alpha and psi. And this is one way in which superfluid turbulence is not very different from its classical fluid counterpart. Qualitatively, everything looks the same. You get these scaling regimes, which roughly these exponents, but of course, they're not determined with very great precision.
Rahul, sorry,
yes.
There's a question from Massimo.
Yes.
Sorry,
yes,
Rahul. Can you? I haven't understood what is the mean angle between particle positions separated by.
Sorry, I should have had a picture. Suppose you're along a particle trajectory, okay? Then you see the vectors between them, and then it is the angle when they are separated by tau.
Okay, thank you.
Okay. Yeah. Sorry, I meant to draw a picture. I'm really sorry about this. Okay. All right. So this was done, for example, for classical fluid turbulence by the Lyon group. Bose, I think, Walter Bose did this. And so, it looks similar, but details. Now there are deviation angles. So what is this? This is something we first studied a long time ago for heavy particles in classical fluid turbulence. It's the angle between the fluid, the Eulerian velocity and the particle velocity. Now, because you have two types of fluid, normal and superfluid, you will have two such angles. And here you can look at log-log plots. And there is some sort of scaling which you can fit to exponents. And the bottom line, if you just want a qualitative takeaway message here, is the normal fluid and superfluid components. They move in the same direction in co-flow superfluid turbulence. So if one of these angles increases phi n, so does phi s. But now there's an important difference. In counterflow, phi n increases, then phi s reduces, okay? And because the superfluid moves opposite to the normal fluid. And all these detailed measurements can be made. I think this will be quite difficult, though the previous one can be done, but to get both the Eulerian field and the particle velocity with good enough accuracy would be a challenge, I think. Now, here is something all of you know. If you have a curve, that's the curvature. And in 3D, you have torsion, you have normal, tangent, binormal. And this is a statistic that has been looked at even in classical fluid turbulence. So you can write down these equations. Please don't look at the details. All you need to know is that in terms of the particle velocities and normal acceleration, you can define the curvature and the torsion. And then you can ask for the statistics of this curvature and the torsion, or rather the modulus of the torsion. And if you do that, you can plot cumulative PDES of these, and they all have very nice tails, power law tails. And the slopes are -3/2 for the curvature case and -2 for the torsion. And this actually holds even in the counterflow. You probably can't see all these details, but all these little symbols means that we have run this with different values of the counterflow velocity. And within error bars, it is these exponents. And there is a way of understanding them which has to do with decoupling joint PDFs of the normal acceleration and the velocity. This is well known in the classical fluid case. And as far as we can see, the same argument goes through, and therefore this beautiful scaling can be understood by making reasonable assumptions about, decoupling, writing a joint PDF as a product of two PDFs. Now, this persistence time PDF, this is slightly complicated, so I won't explain it completely, but all of you know about QR plots. So Q is related to the trace of the velocity derivative matrix squared, and R is the trace of the cubed And from it, you have 4 regions, A, B, C, and D. So A plus B are regions that are dominated by vortical structures. So you can ask, what does this PDF do when you are in this regime? And they all decay exponentially, roughly. Slight variation here. And they certainly decay exponentially. And in a paper that we wrote several years ago, I think with Prabhaditto, Akshay, and probably Prasad, I forgot, we can interpret this decay time as the time that the particles spend in vortical regions, and then they leave. So we have the statistics of those times. So to a first approximation, the same thing continues to happen in this superfluid turbulence, but the actual times change, and here even the form is changing a bit as we change rho sub n. You see, changing rho sub n is tantamount to changing the temperature. So the lower the value of rho sub n, the lower the temperature. Okay, but this is a hard measurement to make in an experiment because you need data on the velocity derivative tensor. You can also do this along particles, and let me not go into details, but this is really something new because this has never been done. And again, you can see essentially it's exponential, and from these exponentials you can extract times which you can identify as the times that the particles spend in vortical regions. And then you can look at its dependence on Stokes, etc., which is given here, but not in complete detail. All right, what more can we do? We can do power PDFs. Why on earth would you want to do this? This is one of the standard measures that is used to characterize the irreversibility of turbulence. So power is acceleration dotted with velocity here, and we have these power PDFs, and you can see they of course have to have mean 0, but we can study them as a function of Stokes. We can study them as a function of the counterflow velocity, and this is how they change. But the important parameter in this business is so-called irreversibility parameter, which is sort of like a skewness of this power PDF. And so here is a plot of the irreversibility versus Stokes for counterflow, co-flow, and this one is even for some light particles. So roughly speaking, this is similar to what is found in 3D fluid turbulence. In particular, this irreversibility parameter is negative. So these things are negatively skewed, and that doesn't change in the superfluid case. And I'm also happy to note that here the experiments have actually been done by the group in Prague. And basically our results are in consonance with their findings, except in some region which they say which cannot be described by an HVBK model. So over the regime where the HVBK model holds, we are in consonance with their results. Okay, so this is the first introduction to irreversibility. Please remember it because I will use it in the third part of my talk. Now, all of you are experts at Lagrangian measurements, so you will ask me whether we have done structure functions along Lagrangian tracks, and we have indeed done it. And from these, you often extract a ratio of the 4th order structure function exponent, the ratio with the 2nd order one, all right? And if you plot this versus tau by tau eta, this ratio should be 2 at very low tau, which it is. And then it shows a big minimum here. So here also qualitatively similar to what is seen in classical fluid turbulence, but of course it depends on details. And there's a distinct difference between co-flow, which is shown in blue, and counterflow superfluid turbulence, which is shown in orange, right? Okay, so I hope you will forgive me for going through it quite rapidly, but I wanted to show you that the whole set of numerical experiments that have been done in classical fluid turbulence to quantify the statistical properties of particles advected by classical fluid turbulence flows can indeed be carried out for the case of superfluid turbulence. Some measurements have been done, some are being done, and some remain a challenge for experimentalists. I hope they will rise to that challenge. Okay, now let me show you a little bit about particles in binary fluid turbulence. So this is something which is in preparation with Nadia. Nadia's great virtue is that he produces results faster than we can write them up. So let me show you one of his results. So first of all, what's the fluid? So I should tell you the fields. So we will use the Cahn-Hilliard-Navier-Stokes equations for this binary fluid mixture. So if it were only Cahn-Hilliard, these two fluids would phase separate, the red from the blue. This is well below TC where they phase separate. But of course, where does this phase separation comes from? From elementary statistical mechanics. It comes from a Landau-Ginzburg functional of this form, where V phi is a double well potential, which I have parameterized as 1 minus phi squared whole squared. And here's the grad phi mod squared term, which takes care of surface tension. And the A-rich phase phi is positive, typically near +1 and -1 in B, and it changes continuously in between them. So if you have a diffuse interface, so here's the double well potential, and you assume that the phi changes only along one direction, y, then you can take a functional derivative, you get that equation. With that boundary condition, you can actually solve it, and you get a tangent hyperbolic interface. This is what we teach our graduate students. But now if you want to put in the fluid, then you have to couple it with the Navier-Stokes equations. So here's Navier-Stokes, and then there are terms here having to do with the action of this order parameter phi that helps us distinguish between the two fluids. And here's a chemical potential, which is related to a functional derivative of the free energy. Still, we have incompressibility. This, if you want to put gravity, minus alpha u if you have friction, typically there in a two-dimensional system. And then here's the Cahn-Hilliard equation, which tells you how the field phi is advected by the velocity, etc. So that's a set of equations. So I promised you fields and particles. So these are the fields we need here, phi and u. And of course, I will not tell you everything about these fields. This is a diffuse interface method, which is a great virtue if you're a physicist, because you don't have to, put boundary conditions in a moving boundary. Of course, an engineer might worry you with other details. We'll get there. Now, the bad thing about the Cahn-Hilliard-Navier-Stokes system is that you just don't have one Reynolds number. You have a Peclet, you have a bond, you have an Ohnesorga, capillary, Kahn, Weber. Kahn is a dimensionless measure of how thick your interface is, and Weber is inversely related to the surface tension. Okay, that's life. You have to face it. We can do direct numerical simulations, many of which are done with CUDA on GPU clusters. And this is some old work that I did with Noirita, Prasad, and Anupam. So if you have a droplet, you see that this is how a droplet behaves. It fluctuates quite a bit. And if you characterize those fluctuations by calculating the deformation of the boundary, I won't define it in detail. It's a dimensionless measure of the perimeter. Then it fluctuates rapidly and indeed is multifractal, and we characterized the multifractality by finding the full singularity spectrum. But that's not what I'm going to talk about today, because I want to put in particles. So here we just put in tracer particles as usual, and we take all precautions. But why did I bring this up? Because so on the left, we have a small droplet of one phase and the other with particles put inside it. On the right, we have a bigger droplet. And you see these particles would have spread throughout the system had it not been for the other phase. But now it's going to take them a long, long time. And this is one of the nicest examples I know of interfaces acting as transport barriers. This is well known, for example, in ocean physics, where there's stratification and there are different layers of salinity, and you get so-called staircases which prevent particle transport. They're known as transport barriers. So here we have a beautiful transport barrier because of this two-phase flow, and it's going on, and all the particles haven't come out yet. All right. So, well, movies are nice for talks, but if you're a scientist, you need to quantify it. So we have looked at a first passage time tau. This is the time required by a particle to go out from the droplet for the first time. And we have plotted cumulative PDES. And to make a long story short, they're all exponential. So you can get a mean of this thing, tau psi. And indeed, as you might expect, this scales with the radius.
Sorry, Rahul. Quick
Yes.
question. In the thing that you showed just before, so the droplet eventually breaks, and is that when all the
No, it's not breaking. No, it's not breaking.
It's a stable droplet.
Well, its surface tension is chosen so that it doesn't break.
Sure.
But there are fluctuations, and so that finally trickle out. Yeah.
I see. Okay, thanks.
And so we can quantify this, and you can do log-log plots, and indeed it does increase with droplet size. And you can completely systematize it. You can ask how does it change with surface tension. You can do the Weber number dependence. It's not very significant to a first approximation. Then you can also ask for the number of particles inside the droplet at time t. Okay, and that decays exponentially, and so on. So, as far as I know, this is the first quantification of this sort of what shall I say? Trapping, or turbulent, transport barrier in a two-fluid setup, which you can, thanks to these equations of particles, you can do in a very elegant way using the Kahn-Hilliard-Navier-Stokes system. We can do it for ternary fluid flows too, but I didn't want to trouble you too much in this talk with more details. And so we can, and we hope that experimentalists will take up this challenge and study this. It should be possible. Now I come to the last or penultimate part of my talk, which is irreversibility in bacterial turbulence. Now again, I don't have, this is the preprint that we have. I don't have time to derive all the equations, but they are well known now. They're even covered in review articles. This is one of the simplest so-called mean bacterial velocity model, in which you have more or less Navier-Stokes, but you have a coefficient lambda naught pressure, and then you have this term, which is now called the Toner 2 term, which depending on the sign of alpha, etc., can either act like a friction or activity, and this is there so that it's stable. And then there are here other terms, okay? And incompressible. You should note, so those of you who are paying full attention, this is not Galilean invariant, but it reduces to Navier-Stokes with friction if all these conditions are met. Okay, so let's look at the terms a bit. We will use periodic boundary conditions because we want to study statistically homogeneous and isotropic bacterial turbulence. We will also restrict ourselves to 2 dimensions because most of the experiments in this field have been conducted in quasi-2D systems. We will work with gamma naught and gamma 2. These were the coefficients, I remind you, of these terms here, del squared and del 4. And then if you do a spatial Fourier transform followed by a linear stability analysis about the spatially uniform states, that will yield wave vectors with magnitude k, which are the linearly unstable modes. You can then also define certain characteristic lengths, velocity, and time scales, which I have defined here. A capital lambda, which is this, a v naught, which is this, and a theta, which is this lambda divided by v naught. Now, these unstable modes can inject energy, excuse me, some typos, into the system. And this then is dissipated by other linearly stable modes and the cubic terms with the coefficient beta greater than 0, and also the linear term with coefficient alpha. If alpha is greater than 0, then it acts like a friction. So if in fact there is energy injection because of alpha, then it is often referred to as the activity parameter, then it has to be negative. But note that there are other sources of activity. If gamma naught is less than 0 and lambda naught is not 1, that they induce activity also. Lambda naught is greater than 1 is used for pusher swimmers like B subtilis. We hold these fixed and we tune the activity principally by varying this parameter alpha. You can also define, all of you I'm sure can do it in your heads, an effective viscosity, which is k squared nu effective, which is all this here. The only new term here, which comes from a sort of closure, which is not our invention, but used in the trade. So you would have to calculate URMS from your calculations, and then you get a new effective. And clearly, if nu effective K is less than 0, then you are pumping energy into the system. If it is greater than 0, then it's acting like a conventional viscosity. So we've done several runs, and I will not tell you exactly, but so this is what things look like. I haven't put all the parameters there in the paper, but I can tell you for different values of alpha, these are the vorticity fields. And I have put in some black dots to show you that we've put in some Lagrangian tracers. And over here below this, I have put in the energy spectra. And the gray shaded region is the region of K where nu effective is less than 0, so where energy is being pumped into the system, and clearly that affects the sizes of your vortical patches and so on. By the way, this one is basically one mode. This has not been studied too much by other people, but I will restrict myself mainly to a class of runs where we just change alpha and we have these types of spectra. You can ask for fluxes, which we have also done. Those who know fluxes will, of course, be able to read off. Those who won't learn about it from this talk. But from all these statistical properties, we can extract a URMS. We can extract an integral scale suitably non-dimensionalized. We can extract an integral scale time, and we can extract an integral scale Reynolds number, and we can plot them versus alpha, all other things being held fixed. So clearly, as alpha becomes more and more positive, URMS decreases, as does the integral length scale, as does the Reynolds number. But this TI goes through a minimum because, you know, it's the ratio of URMS and things, and so one decays faster than the other, so you get this interesting effect as a function of alpha. But this is all Eulerian for the moment. We want to do Lagrangian measurements, and all of you know that if you look at a movie of Lagrangian particles in a turbulent flow and you play it backwards and forwards, then to the unaided eye, it's not very trivial to figure out whether it's going forward in time or backward in time. So it's sort of clear what you should do, and it was first enunciated in a paper by H. Su and his co-authors, including Alain, if he's still in the audience. They call these flight crash events, and somewhat later, Akshay Bhatnagar, Dhruvaditto, and I, and etc. showed that basically, this is what happens. That heavy inertial particles in turbulence gain energy slowly but lose it rapidly. The way to analyze this is by using these increments along particle trajectories, either energy increments, or you can look at the pressure, which I already alluded to when I showed you data for particles in superfluid turbulence. And it is found that typically these PDFs are skewed, and on average they're skewed in such a way that in classical fluid turbulence they lose energy faster than they gain it. And as I showed you, this is also the case in superfluid turbulence. Now let's look at what happens in bacterial fluid turbulence. So we characterize irreversibility by using this mean bacterial velocity model. We uncover an important qualitative way in which this is different from its fluid turbulence counterpart. In particular, for large positive and large but negative values of alpha, that is either big friction or big activity, the PDFs of these quantities are positively skewed. So irreversibility in bacterial turbulence, particles typically on average gain energy faster than they lose it for certain ranges of values of alpha. So this is yet another way in which they're different. I mean, Samriddhi and his co-workers had a nice way of studying this very model where they showed that with very high activity, you've got anomalous diffusion. So here, I don't know whether you can see this very well. Probably I can blow it up for a moment. This is a plot of the energy versus time, and the sort of so-called flight crash event, gain energy slowly, lose it rapidly. But here we have many instances where you are gaining energy rapidly and losing it slowly. And how this happens precisely depends on the activity parameter alpha. Okay, so we have plotted here the skewnesses of the power distribution and the W distribution. And, the blue is the range where the skewnesses are positive, and pink is where they're negative. So very large activity or very large friction, you get the effect which is the opposite of what is seen in classical fluid turbulence. I could show you PDFs of those, and you can see clearly that they are skewed. This is the conventional way of plotting it. The solid line is for positive and dashed line is for negative, so they're clearly different. And I won't go through all the details, but when you distill from these the skewnesses, you get what I showed you on the previous slide. You can try to condition this on the Okubo-Weiss parameter, which is defined here. It's sort of like QR, but for 2D. And then you can condition this PSK, where is it positive and where is it negative? And it is more so in regions where you have a positive value for this, which is vortical rather than where it is extensional. By the way, this thing is actually a power law. This Samriddhi and his group had also got that you can extract a power here for this Okubo-Weiss parameter for certain ranges of values of alpha. You can have a power law here as far as we can tell. Okay, so here are conclusions for this part that the mean bacterial flow model allows us to study reversibility in bacterial turbulence. And I think the experiments can be done because we increase activity by increasing alpha. But in experiments, it can be increased by enhancing the oxygen that is supplied to the bacteria. And the typical velocity scale is this, square root alpha over beta. It's a measure of the swimming speed of bacteria. This has been worked out nicely in a paper by Sanjay and Joy. And then if you're in the frictional regime, you can tune alpha by changing either bottom friction or air drag induced friction. So we hope that our studies will encourage experimentalists to look for reversibility in bacterial turbulence. Let me just show you one last thing, which I will not cover, because you see, so far I have been looking at particles that are passive, they do not affect the flow. But you could ask, don't particles affect the vortex tubes and so on? And indeed they do. And we wrote down a nice model several years ago with Vishwanath and Marc Brachet. And okay, I don't have the time to cover it, but these being active particles, you can study far fewer than we can with passive particles. And this work has been taken forward into the third dimension. These were all two-dimensional by George Kristolovich and his student Onorato, I think, if I'm not, no, might be wrong. Okay, so for the moment, let me, Umberto, excuse, thank you. And if somebody wants, I can discuss this later, but for the moment, let me thank you for your attention, and I'll be happy to answer any questions that you have.
Thank you, Rahul. Questions? Massimo.
First of all, thanks a lot for the very interesting talk, Rahul.
Thank you.
It was while we were speaking about the last topic, so the bacterial turbulence.
Yes.
And in particular to the transport of particles by the velocity field generated by bacterial turbulence.
Yes.
There is something which I always I had been thinking in the last few months, because essentially, especially when you put the particle in active fluid with bacteria moved by bacteria,
yes.
I mean. I'm not sure. I mean, at least I would like to understand if, in your opinion, a continuum description as the one that you used for the fluid can catch all the phenomena that you may have for the transport of the particle in such fluids. Because I mean, in that case, you will have bacteria which will.
I understand. So already, I understand what you mean. But all I'm saying is we have already made the approximation of using the mean bacterial velocity model, where everything has been reduced to one velocity. You can, of course, write down more general models, and the conditions under which you get to this is discussed in some of these papers, these big review papers that I have written. Once you have those, then you are asking, what is this U?
The discreteness of the, yes, exactly.
Yeah. So, I mean, people who write, I mean, including our chair of our session, he's also used this, if I'm not mistaken, with Lagrangian particles and found anomalous diffusion. And the claim is that that will also do. So it's possible that there is some subtlety of the sort that you're mentioning, but as a first approximation, I thought this was a good thing to try. So nothing.
Sure. I mean, we were just if you thought about the possible effects coming from essentially the collisions between, I mean, the active particle and the colloid that you put there.
No, the particle is not active.
Oh, the tracers, whatever. Yes.
It's just tracers.
Sure.
Model is active.
Sure.
The underlying, right.
Ganesh, you want to go ahead?
Thank you, Samriddhi. Thank you, Rahul, for the talk. Actually, my question was regarding a particular detail in the first part of your talk, where I think you had written the friction force that was acting on a vortex line, and it seemed like it consisted of two terms. One had a Magnus-like form, but the other had a Magnus crossed into a vorticity further.
Yes, right.
Yeah, okay. And I was wondering what the first term meant. So I think the second term, if correct me if I'm wrong, but the second term is intuitive in terms of a lift-like force.
Yes, you're right. Okay, so I always get this. Sanjay, are you around? Is Sanjay there in the audio?
Yeah. Can you hear me?
Yes.
Yeah, we can hear you.
Can you remind me as to where this other term comes from?
I think the first one is because there are two things. First one is, as he said, it's a Magnus force, second term basically. And there is a second thing called drag between the two components.
So could you repeat it? What? There is a second?
Suppose there is a vortex moving in a background superfluid. So it's just a drag force between the two. And the vortex and the coming from the fluids. It's a drag force. So drag force is in the direction of velocity. That's why you have taken the cross product with a unit vector of omega.
Okay, but so you're saying the term proportional to B is the drag and the term proportional to B prime is a Magnus-like lift. Is that correct?
Yeah.
But the drag is not a linear drag. It's proportional to the product of the vorticity and the slip velocity. That Okay.
So that's why it's unit vector, not to make it tend along the direction of velocity, slip velocity.
Right. Okay. I actually had one more question about the same thing, where you had mentioned that you choose a small but finite value for the kinematic viscosity of the superfluid.
Yes.
And so the question I had was, if you define a topological invariant like helicity for the superfluid, would it be conserved for nu-s? I think you mentioned the fact that a small finite.
Yeah, right. I mean, ideally, you would just like it to be Euler for the superfluid.
Right.
Aside from the mutual friction.
Correct.
But right. But often we put it, the numericists put it for numerical stability.
But is there an issue of sensitivity to the ratio of nu-n by nu-s? Are things insensitive to that?
Well, to the extent that we have tried, yes, but you see, we cannot do it very much. The reason is similar to carrying out, let's say, MHD simulations at Prandtl numbers that are very different from one, because one or the other dissipation range will not get resolved properly, and that will lead to instability. So there's a practical consideration. We have used 1/10 in most of our runs.
Okay, thank
you. Any other questions? Comments? No. Okay, we are dot on time, as it were.
Okay, yeah, I timed myself. Okay, good. So timers help.
There are 15 minutes, 10 minutes to discuss things. So again, thanks very much.
Should I stop? Thank you. Shall I stop sharing?
Yes.